So in today's lesson, we're going to learn about similar triangles. This is likely a concept that you have seen before in previous math classes, but we're just going to remind you of this because it does come in handy as we work through trigonometry. So we're not quite going to start trigonometry yet. That's coming in the next lesson, but this is another prerequisite skill that will be important for you, and it'll remind you of a few conventions that are important in math. So first of all, we say that two triangles are similar if they have a couple of necessary properties that relate them. So the first is that the triangles are similar if they have all angles that are equal. That's the first. All the angle measurements are going to be of equal measure. And the second piece to that is that the sides are what we say proportional. The side lengths, I should say, are proportional. Now, what does proportional mean? It means that the ratio of the sides is the same value. And I'm going to talk about that in a little bit. But before we move on, there are a couple of conventions that I want to talk about. So the first is that here what we've identified, I have two triangles, I have the blue one and I have the orange one. And I've intentionally not labeled the orange one yet. I want you to notice that I've written triangle, the symbol triangle, ABC. And so I want to go and see that. So there's A, there's B, and there's C. So the capital letter represents the vertices of the triangles, or the corners. And so we're saying triangle ABC. So this little squiggly line here is a symbol that we use in math to indicate that the triangles are similar. So this would read as triangle ABC is similar to triangle DEF. Now this does not mean that they're equal, because even though all the angles in these triangles are equal, the side lengths are clearly not equal, but they are proportional to each other. So now let's start by labeling the orange triangle. I have triangle ABC is similar to triangle DEF. And how we write that is very important. And the order in which we say it relates to how it needs to be written when we go and draw those letters on our diagram. So for instance, corner A or vertex A is of the same size as a vertex D or corner D, which means that when I go and I label my triangle, I'm going to label this as D. So the order there needs to relate. So for instance, if I'm going A, B, C, then I know that this corner right here is going to be the same size as corner B in my blue triangle. So let's relate those as well. So angle B is going to be the same size as angle E in my orange triangle, and so on and so forth. And if these are positioned nicely so that they're the angles are kind of in the same position. But we'd often see that one or both of the triangles are sort of rotated in odd directions. So we can't necessarily go clockwise or counterclockwise. We have to be careful about that. Okay, but nonetheless, the way that we write this in matters is what I'm trying to say, because what you're identifying by the order of the letters is which angles are of the same size. Okay, so really important. Now, another thing that I want to mention that is an important convention is that there are two different ways of identifying how side lengths are represented. So here I have AB together. Sometimes you'll even see like a little line on top of them just to indicate that it's a line, but not always. And so in this case, side AB is how we've written it. But you need to know that in some questions, in some questions, what you'll see instead, notice that the corners are uppercase letters, but sometimes the side lengths are referred to by small lowercase letters. So because angle C is opposite this side, okay, so if I went like this, here's this corner C, and I went to the opposite side of it, then that side is another way to refer to side length AB would be side little c, which is, I'm trying to emphasize that it's a lowercase, right? And so given that, well, what would I call this side opposite angle B? Well, I'd call it side little b, but an alternate way to describe that would be to call it side AC in uppercase letters, and so on and so forth. So then to follow that along, corner A, big A, is opposite side little a, which can also be referred to as BC. Okay, so there's that. So there's something else that I wanted to talk to you about. And in order to do that, what I'm going to do is just to erase some of what I've written here and start from the get-go. Now, you'll remember that I described how the order of the letters tell us which angles are related. So I know from the way that my letters are indicated here that angle A is going to be of the same size as angle D. So one way to represent that is to kind of just draw the little line in there like that. But that, knowing that about the angles, that also tells us which sides are proportional to each other. So, it's obvious from this simple example that I'm giving you which sides are going to be proportional. I think you can probably deduce that BC is going to be proportional to EF. But, the diagrams aren't always so nice and conveniently positioned. So we need to have a different strategy for when it's not so obvious. Okay, so we find the angles that are identical. Okay, we've done that. A and D are the ones that are equal in size and measurement. And then we locate the side opposite those angles that are equal. So I go opposite, and that is what's telling me that BC is proportional to EF. Okay, and so we can see that if we look at this proportionality statement here. So what this is trying to tell us is that AB is proportional to DE. Well, let's look. AB, I'm going to write that in, I'm going to highlight it. AB should be proportional to DE. And look, the angles that are opposite those sides are equal in size. And so, we've already talked about BC being proportional to EF. That's this right here. And then lastly, we have AC being proportional to DF, right? And so that's all we're saying when we set up this little ratio here. We write out, and notice that all of the sides from the first triangle, right? So here's triangle number 1, here's triangle number 2. Notice that all of the parts that belong to one of the triangle are on the same side of the denominator, okay, the same side of the fraction in the numerator, and then all of the sides of the second triangle are all in the denominator there. Okay, so they're all on that same side of the fraction. Okay, so now I want to get rid of some of this too and keep going. And I think the introductory part for this might seem a little long to you, but the details are important, and you're going to see how that plays out when we look at our example. So let me just get rid of some of this writing here. Here we go. Perfect. And so now let's go back to this little ratio here to show you what I mean by that the side lengths are proportional. I'm just going to make up some really convenient numbers here. So let's just say, for example, that side AB had a side length of 12, and side DE, which is the side that is proportional to it, has a side length of 6. So that would mean that the ratio of AB to DE I can get by simply filling in those values, 12/6, which happens to give me a 2. Now, that will help me solve for any of the other sides if I happen to know the value of that side. So let's say, for instance, over here, EF is 4. That will allow me to solve for side BC if I so desire, right? Because the ratio is the same. So another way that I could have done that was to just, was to say, I know that AB is proportional to DE, and I also know that BC is proportional to EF. So now I'm going to fill in what I know. And so really, I have a situation where I have 1, 2, 3, 4 pieces and only one unknown, and that's a situation I can solve. So I'm going to substitute in the values that I have for each. So AB is 12, and DE is 6. BC is what I don't know, so I'm just going to leave it as BC. And then EF I've said is 4. So I can choose to solve this in whichever way I want, right? Bringing the 4 up and multiplying. In some cases, if my unknown is in the denominator, I might want to cross multiply to solve as a solution. And then I can kind of go from there. Now, these are some nice numbers. I can see that the ratio is just going to be, a triangle ABC is twice, the side lengths are twice as big as the smaller triangle. So, it would be easier for me to probably just mentally see this. But keep in mind that the side lengths in a lot of cases are going to be not super nice numbers, potentially decimals and so on and so forth. So this is a strategy that will work when the numbers aren't so friendly. Let's look at an example. All right, so here's our first example. Given triangle ABC is similar to triangle DEF, find the measure of angle C and the length of DE. So I always find it helpful to identify which sides are the ones that are similar or proportional before we start. Now, we can see here that when I look at this triangle, A is going to be the same size as D, and B the same size as E, and C the same size as F. So A, B, C, D, E, F. These are nicely organized in a way for me to see which sides are going to be proportional. So in this case, it's fairly obvious, so I don't need to necessarily do this, but a strategy that I have used with some complicated questions where the triangles are rotated or whatnot is to just sort of highlight in a particular color the sides that are proportional. This just is a way to visualize that pretty clearly. And like I said, in cases where the triangles are rotated. So part of this is going to be fairly straightforward. I can see that, angle C is the angle that I want to know. That's this guy right here. And I can see that based on the position of this triangle, that angle C is going to be equal to angle F. And since I know what angle F is, it's 42 degrees, then I've solved for that part of the question. So I can say I've done that part. Now the other piece that I need is to find side DE. Now, let's look at what information I have. So I have side BC and EF, and those are two sides that I have information for, and they happen to be proportional to each other. So that is handy. And the other side that I have is side AB, which is proportional to DE. So DE is my unknown. So I'm going to set up a proportionality statement that will allow me to solve this. Now, you'll remember that I want to have all the pieces on the same triangle on the same side of my fraction when I built this. So I know that DE is proportional to AB, and I know that EF is proportional to BC. Right? I can see that from my sides here. And so now I'm in a position where I know 3 of these pieces. Now just to double check, DE and EF are on the same side of the fraction because they're in the same triangle. And then same with AB and BC. Let me just substitute in the values that I have here. So DE is my unknown, so I'm just going to leave that as DE. AB is 12.1. I'm going to leave out the units and just remember them for the end. EF has a measure of 14.1 and BC is 20.1. And so now all I need to do is just simply isolate DE and solve for it by bringing up the 12.1 and multiplying by it. So DE is going to be equal to 14.1 over 20.1 times 12.1. And since all of my other measurements are rounded to the nearest tenth, I'm going to do the same thing with my final answer for DE, although it isn't specified in the question, so it's difficult to really say. I'm going to go 8.5 centimeter. Was it centimeters? Yes, it was centimeters. And so there we go, and we've solved for side DE. All right, so 8.5 centimeters. Now, sometimes it's worth your while to say, well, does that answer make sense in the context of the question? And it appears to do so, though the diagrams are not always necessarily to scale. So there's one example. Let's look at a second one. All right, so in this diagram, it says that DE is parallel to AC. Here's AC. And it says find the length of AC. So I want you to pause the video and I want you to try this question just to see if you have any strategies of your own to try and work through it. And in a minute, I'm going to come back and tell you some things that I notice. Okay, so the first thing that I notice right away is that I appear to have a big triangle and a smaller triangle inside of it. And so because they've told me that AC is parallel to DE, that helps me to know that I can therefore say that, okay, well, I have this big triangle inside of a smaller one, right? Big triangle and then smaller triangle, and those triangles are going to have to be similar because their angles are going to be corresponding, right? Do you remember the parallel line theorem and how there's that F pattern there? So that tells me this angle here, angle D, is equal to angle A, and angle E is going to be equal to angle C. So that allows me to make a statement here. That allows me to say that triangle ABC is therefore similar to triangle, let me see it, DBE, right? ABC, and now I'm going to go with a smaller triangle, DBE. So that's my proportionality statement, or my similar triangle statement. Right, so you may find it helpful to do what I'm about to do, which is to kind of create a little copy of the smaller triangle and put it sort of over the side, and then I can sort of ignore the smaller part, this 36 centimeters in the smaller one, by maybe kind of I can either redraw that or just kind of do this where I get rid of it. There we go. So there's big triangle and little triangle. All right, so what am I trying to find here? Well, I'm trying to find side AC. That's this guy right here. Right, there's side AC, which I can tell that both AC and DE are opposite angle B, so those are my sides that are corresponding. So now, in order to solve for this, I need to know which other sides are corresponding. And so I have side AB here. Here's AB that is proportional to DB. So I can set up a proportionality statement here and solve for it. So I know that AC, side AC is proportional to side DE, just as side AB is proportional to DB. And now I can fill in some of the information and solve. I'm going to make this a little bit smaller. There we go. So AC is my unknown. What is side DE? DE is 36. Side AB, remember I need to know the measure of the entire side here. So that's going to be 48, 58, 59, 60 centimeters in length. So that's what I'm going to put in here. So 60 centimeters. And then DB is, of course, 48. So now I'm in a situation where I just need to isolate AC by bringing my 36 up and then solving for AC. It's going to be 60 divided by 48 times 36. I'm just going to grab my handy dandy calculator. And when I go through this, I am getting 45, and the units are centimeters, so 45 centimeters. So there we go. And so is that an answer that makes sense in the context of this question? Well, it looks like it does. So I think I'm good to go. So I'm hoping that you adopted a similar strategy and were able to solve that reasonably well. Let's look at another question. So this is a case where I have, my triangles are rotated, and in this case, maybe the sides that are corresponding are a little bit obvious, but this is an example of where there's a rotation, so we want to be clear on which sides are corresponding. So first of all, in this question, they're asking us to find the length of FG. So I'm going to go ahead and highlight FG. And in order to create my proportionality statement, I need to know which sides are corresponding. So I can see here that, these two lines are intersecting, and that creates these opposite angles. Now, from grade 9, you should remember that when that cross happens, the opposite angle theorem tells us that this angle here is equal to this angle here. So if that's true, then I'm just going to go ahead and put 43. Oh, that's 43 degrees in there. But that also tells me which sides correspond, which, is not so, is fairly obvious anyway, but if this angle is equal to that angle, then that means this side corresponds to that side. Also, I can see here that they've indicated that angle G is a right angle and angle H up here is a right angle. That means that the corresponding sides, or the proportional sides, are going to be opposite that. So that means that these sides are corresponding. So I'm going to go ahead and highlight them in green to show that they are corresponding. And of course I have one side left, so that makes things fairly simple. I can go ahead and highlight those sides. So there, I've highlighted all the sides that relate to one another, and so I can sort of create my proportionality statement now. So I want FG. FG is what I'm looking for. And what is it proportional to? Well, it's proportional to HI here, so I'm going to write that in. And then, so where are my other two pieces of information? Well, it looks like I have FG, oops, FG, FJ and JI. And so since those are the sides that are proportional to another, and I have both of the lengths of those, that's going to allow me to solve for my unknown here. So let me set that up. And again, remember, I want to have all the pieces of information from the same triangle on the same side of the fraction. So that means that what I'm going to put up here has to be from the same triangle as side FG. And so for me, that's going to be FJ. So Fj is proportional to Ji. So let's fill in some information here. So Fg is my unknown side. Hi is 4.3. Fj happens to be 18.9. And then Ji is 6.3. So now I'm going to just, take my 4.3 and move it up and multiply by it. So Fg is going to be equal to 18.9 divided by 6.3 times 4.3. Grabbing my calculator to calculate that out. I'm getting 12.9. So let's just double check that that makes sense in the context of the question. 12.9, I'm looking at the rest of the sides. That seems to make sense, so I'm in good shape. So this note has 3 more problems with it. They're sort of more word problems, but I think that they're fairly straightforward. In the interest of time, what I'm going to do is I'm going to create a solution to these 3 problems so that you can refer to them, read over them, make sure that you understand them, and then proceed with some of the practice questions. And as always, if there's something that's not clear to you, make sure that you reach out. If you do struggle with the word problems, worry less about that. Just get down the similar triangles problems on their own without worrying about the word problems. That's the priority here. But if you do have the time and you want to test or challenge yourself, feel free to try the word problems.